Hello, everyone. Hello to this edition to Global's R&D. For those of you who don't know me, I'm Rosti, and I'm the team lead of the networking team in DFINITY. And today I have the pleasure of hosting the meeting. So we have like a pretty exciting agenda, and without further ado, let's dive directly into it. So first, it's Kyle with Metrics.
Thanks, Rostislav. I want to get to that community demo from TAP, so I'm going to go quickly. Really excited for that. So the NNS approved an update to our pricing structure on the internet computer. I want to just provide basically that change in data so that you can kind of see how that affected. Here is the cycle burn of the SNS subnet, and you can see pretty clearly which day the NNS executed that protocol change. I actually had to choose the SNS subnet specifically because most of our other subnets are the data is a lot more variable, and it's actually harder to see this change in data. So this change in cycle costs. So just keep that in mind. It's not like you'll see this on every single subnet, but more just wanted to show exactly how these kind of pricing changes take effect, and that the SNS or the NNS's vote really does matter. And so really appreciative of how serious the DAO takes its responsibility. So that's one topic. Next topic I wanted to go to on the next slide. I want to do the, if you know the meme of how it started, how it's going, I wanted to do that, but for 2024 for the internet computer. So I have here a list of probably what you might call like the top 5 tier 2 metrics for the internet computer. Cycle burn is easily the most important. That's the clearest indication of growth. And I've mentioned on these calls time and time again, ad nauseum, that cycle burn has just been going through the roof. But I want to give you guys an idea of what the tier 2 metrics look like. So and I want to do it in a fun end of the year kind of way. So here you see how 2024 started for things like the number of canisters, the number of internet identities. Side note, I took out the amount that I think are just bots. So if the number looks different than the dashboard, that's why. Cycle, ICP burn, canister state, and CKBTC volume. So these are the numbers coming into 2024. And if we go to the next slide, you'll see how we are doing as of November 26th. And you can see, I mean, just through the roof. Every single metric just showing a lot of growth. So that daily change column, that's basically if you take the daily average before 2024 and compare it to what we've done in 2024, and you can see not only these metrics going in the right direction, they are accelerating. So really, really good positive indication there. Again, I want to get to this TAP protocol demo, so I'm going to end here. And if you have any questions, feel free to drop them in the chat, and I'll be lurking around and answering them there. Thanks.
Thanks, Kyle. And next, we go to actually another pretty exciting update that Manu is going to give us about all the achievements on the core protocol in the last few weeks.
Yeah, hey everybody, thanks Rosti. Yeah, I'm going to talk about some milestones that we achieved that I think are very exciting. So we have internetcomputer.org/roadmap where we outline what we're trying, what technical progress we're trying to make on the internet computer. And in this month, November 24, we reached 3 big milestones actually, called Tokamak, Stellarator, and Beryllium. And we're now going to take some time diving into each of them, and I'm going to have some experts join me to explain the details. But I'll start maybe a bit more high level. And I'll start maybe about the ICP vision and how this fits in. So if you've looked at the most recent deck that we used to explain ICP, I took some quotes here. It says, ICP makes the internet into a world computer and build anything on the internet. And if I have to explain this in my own words, I think how I understand this is that like Bitcoin and Ethereum really prove the value of how secure things can be running software in a distributed way with a blockchain, decentralized. But we see that still today, the applications are mostly like small financial applications, and we think you could do much more. And so ICP's vision is really trying to push that boundary and enabling developers to build big advanced applications on chain, taking advantage of that security, taking advantage of the financial tokens that you have because of these blockchains. So really push the boundary of what's possible. And we're going to talk about 3 big milestones that together, I think, really help advance what you can build on chain. And the 3 milestones you can summarize as they're about speed, simplicity, and storage. Speed is going to be about tokamak, which is purely about reducing end-to-end latency, making things nicer to use for the users and enabling more latency critical applications. We're going to talk about storage in the Stellarator milestone, which enables applications that need a lot of memory on chain. And we're going to talk about simplicity with the Beryllium milestone, which gives devs the tools they need to build advanced applications on chain. We'll go over them one by one, and let's start with tokamak. And here, actually, Rosti is going to talk us through the details.
Yeah. Hello again from me. So in the next few minutes, I'll shed a bit more light on the tokamak milestone. But first, I want to start with a small note. So Manu already spoke about the work computer, and this vision is actually a general compute platform that can run any software. I mean, this is just a reminder of a thing that most likely most of you know. And this software are smart contracts, and this is how we usually code them. So what you see as an improved observable latency is the result of improving the ICP platform, and not by improving, individual smart contracts. So the milestone has landed, and let's get right into some of the achieved results. So the graph that you already see depicts the time distribution of how long an ICP transaction takes done via the NNS DApp. So this is the time it takes to send ICP from one address to another, and the time is measured directly from the browser. So in the figure, you can see that we achieved nearly 50% speed up. So for example, the mean latency before was around 4 seconds, and now it's around 2 seconds. A fairly important measure that often gets neglected is the tail latency. So this is basically, if you get very unlucky, how much you have to wait at most until your transaction gets through. And this is also down by nearly 50%. It was around 15 seconds before, and now it's down to 7.5 seconds. Next result that I want to show is the distribution of end-to-end latencies for the internet identity sign-in times, measured again from the user browser. So most of you are also familiar with the internet identity. This is the authentication service running on the internet computer. And here again, you can see an improvement of around 50% for the mean. Before it was around 7 seconds, and now it's closer to 3.5 seconds. An interesting thing to note is that the relative tail latency improvement is not that impressive, but this is because the protocol improvements are marginal compared to the latency of the whole flow of II sign-in. And I'll get to that in a bit. And as a third example, I want to show you a bit more theoretical example. So this is the latency distribution for an update code to a no-op or like super fast Canister on application subnet. There you can clearly see the 50% improvement both on mean and tail latencies. But the important message that I want to convey with this graph is that the ICP platform overhead is around 1 second on average. So this makes it one of the fastest in the industry. After that, what constitutes the rest of the observed user latency is the actual duration of execution of the Canister code. So this is the reason why there is a small relative improvement of tail latencies for the II sign-in example. So people may think that 1 second is too big of an overhead, but don't forget that within this 1 second, one block is being finalized and the state is being certified. So I think it is a pretty good target. So next, I want to talk a bit about why we did the milestone. So of course, the results that you see is one of the main reasons. So namely, we really wanted to improve the user experience of the platform, so dApps feel much more responsive, and user interaction is really a pleasure. So I'm yet to meet someone who likes staring at spinning wheels. Another reason, or actually a consequence of the tokamak milestone, is that we did also make the developer experience on the IC a bit more closer to a Web2 service. So there are 2 dimensions to that. Response times do improve the developer experience, of course, but there is the indirect result of the milestone, and that is that developers have access to asynchronous update calls as part of the protocol, which I'll touch on a bit in the next slide. Last but not least, I want to mention that we want to be leaders in our industry, so our solution does provide one of the fastest end-to-end experiences. So in the last year, end-to-end latency has become a very important metric. And in my opinion, this is great because, you know, finality and block rate, depending on the definition, can be fairly meaningless to the user. So for example, what's the point of fast finality if getting your data into a system is slow or reading your data out of the system is slow? So I think measuring end-to-end latency is actually a thing in the right direction overall. Oops. So how did we achieve all of this? Firstly, we did introduce the synchronous update calls, meaning that the HTTP update call now returns a result with a certificate on success, making polling the replicated state a bit obsolete, making it not a bit, but completely obsolete. This semantics is familiar for people that use Web2 infrastructure services, and we wanted to make the experience on the IC similar. So this synchronous behavior is something that makes the interaction with the system faster and development much easier. So the second enhancement that we did was on the improved boundary node routing. So before, the boundary nodes were routing requests to replicas in a round-robin fashion, regardless of their distance to the replica. Now we have improved this, so we always route to a set of replicas that are close by. And thirdly, we have improved the configuration of our consensus algorithm. So more concretely, we decreased the notary delay duration, which people can think of as a throttle to the block rate. So this throttle is actually an important synchronization gauge that allows stable functioning of the protocol in all conditions. And decreasing the notary delay didn't sacrifice any reliability in any way. And it was actually made possible thanks to the complete rewrite of the P2P layer. So in the QR code that I have attached, you can read a bit more about the technical aspects of the milestone. Also in the blog, you can find the technical paper of the new P2P design as well. And with that, I can hand it off to the next speaker, which will present the Stellator milestone.
Yeah, that's amazing, Rusty. And fun fact, I was just browsing Tagger today, and they just upgraded to take advantage of this new endpoint, and I saw a lot of comments about how snappy it felt. So that's really cool. Then this was the tokamak milestone, so speed. Let's move on to the Stellarator milestone about storage. And here we're going to talk about three key ingredients. One is increasing how much memory each canister can use and how much you can store on a single subnet. Then we're going to talk about increasing the bandwidth. So you don't just get more storage, because you can also have a bigger, more bandwidth to get stay there. And we're going to talk about simple and scalable persistence in Motoko. And luckily, I get to call in three experts again to talk about these 3 points. So I'll first hand it over to Stefan to talk about these increased limits.
Hello, everybody. I'm Stefan from the message writing team. There is one slide earlier that you skipped, Rusty. Yep. So one part of the Stellarator milestone is that we increase the memory limits of an IC replica. Both the subnet memory limit, which is how much data a subnet can store as a whole, as well as the canister stable memory limit, which determines how much a single canister can store. And this picture gives like a historical view of where these limits were. At genesis of the internet computer in May 21, there wasn't really a formal subnet state size limit, but realistically, it could do maybe 50 gigabytes, something around there. And ever since then, it has increased steadily. Now the Stellarator milestone is the most recent step here from 700 gigabytes to 1 terabyte. But crucially, it's much more than that. It lays the groundwork for future improvements beyond that. Similarly, the per canister memory limit, we started at 4 gigabyte. That's the stable memory. Heap is separate. So it started at 4 gigabyte, and now it's at 500. That's a 125x improvement over these last few years. Next slide, please. So as you can see, we've been improving these limits continuously, and we will continue to do so. And the reason why we do that is, of course, we want people to use the storage. There are dApps that just require a large amount of storage. The list is endless of like dApps that need that, but I'm thinking here of like AI applications that might rely on large models, like storing images, NFTs, maybe games. Yeah, like I said, the list is endless of what you can do with storage. But another point here is that we also want to make better use of the resources that we have, because all of these improvements are more data stored on the same hardware, which also means that if there is more data on a replica, then the IC can charge more cycles for all the storage it provides, and ultimately that leads to better tokenomics. Next slide, please. On a more thank you. There is on a more technical level, like what allowed the IC to like increase to the state size limit is the new storage layer. The bottleneck that kept us at 700 gigabytes was checkpointing. Checkpointing is the part of the replica process that writes the state to disk. And before Stellarator, with the old storage layer, it had like two very unfortunate properties. One was checkpointing would take longer and longer the larger the state, which naturally like imposes a limit on like how large the state could get with reasonable checkpointing times. But even worse, because it was implemented in a way where the heavy lifting was done by the operating system or the file system, it actually meant that there was very little to optimize step by step, because all the heavy work was done in somebody else's code. And in fact, we didn't see, like there wasn't much room to go beyond 700 gigabytes with this old storage layer. In fact, 700 gigabyte was already kind of pushing it, to be honest. There was very little safety margin there. So instead, with Stellarator, we introduced an extensive redesign of how storage works around a data structure called Log Structured Merge Trees, or LSMT. And the rollout of that improved checkpointing considerably. For example, on the Bitcoin subnet, it went from 20 seconds to 1 second. And the main technical improvement that it provides is that checkpointing time is much less sensitive to state size. However, that doesn't mean that checkpointing is always fast either. There are, of course, other dimensions, number of canisters, number of messages, etc. So that's where the other improvement comes in. It gives us much more control over what runs when and how to improve performance going forward, which opens up the whole range of follow-up improvements. And in fact, later in this presentation, Alex will give a progress report on one of these follow-up improvements. Yeah, thank you.
Cool, then we're going to jump right into the second Stellarator feature. Camille, please take it away.
Right. Hello, everyone. My name is Camille. I'm an engineer on the consensus team, and now I'm going to talk about a conceptually simple improvement we made in consensus algorithm in order to make the throughput three times higher. Let's go to the next slide, please. Yeah, so here you can see the comparison between the previous implementation on the left and the current one on the right. So like in the experiment I ran, I was sending a bunch of big messages to the IC, and in the past we were bound by 2 megabytes per second. So this was how much ingress messages were sent to IC. On the right, you can see the current behavior. So right now, it seems that when we send big messages, we can achieve a throughput of around 7 megabytes per second, which is roughly a 3x improvement. On the next slide, you can see the same experiment, but repeated for small messages instead. So whereas in the previous one, we were sending messages of, say, 2 megabytes, here we send many messages of size 4 kilobytes. So here you can see on the left side that we were still bounded by 2 megabytes per second, but right now we are bound by roughly 6 megabytes per second. So it's roughly lower than what we did saw for big messages, but it's still 3x improvement. And on the next slide, I'll tell you why we care about this. I think it's pretty clear, like having more throughput means that users can upload a large amount of data faster. It could be either an AI model or a big collection of NFTs or a long video. And from the IC ecosystem point of view, it's also beneficial because now replicas could utilize the bandwidth more efficiently, which means that more ingress messages can be passed to the consensus, which means that more cycles can be buried in the end. Now I'm going to tell you how we achieved it. So let me remind you like how the ingress messages were handled by the IC in the past. So in the past, like when a user send an ingress message to the IC, first it got into like, first we had to send it to the boundary node, then the boundary node chose a peer on the subnet in some way, send the message there, and then one of the peers who received the message broadcasted the message to everyone on the subnet. Later on, when some peer became a block maker, he would put as many ingress message into block as possible and serialize the block and send it to everyone else on the subnet as is. Even though the peers might have already had all the ingress messages in the pools. And on the next slide, you'll see what we changed. So we didn't change the way we broadcast the ingress messages, we changed the way we broadcast the blocks instead. So we still put the ingress message in the block, but before we send the block to the peers, first we strip the ingress messages from the block and replace them with the references or the hashes. So now, like if I'm a peer who receives such a stripped block from a block maker, I'm going to reconstruct the block by replacing all the references by the referenced ingress messages, by either taking them from my ingress pool or by asking the block maker for the missing ingress message. And on the next slide, I'll tell you why this makes such a huge difference. So on this graph, you can see the bandwidth utilization before. So the yellow bars depict the bandwidth utilization of ingress messages. So those are like, this is how much bandwidth we use to send the ingress messages around. The green bars represent the bandwidth usage by the consensus itself. So you can see there are like those 7 spikes or 6 spikes, I cannot count. Like this means that this is like just, this is from one peer point of view. Like, so those 6 green bars means that a particular peer was selected as a block maker in those 6 particular points of time, and they had to send a huge amount of data to all the peers. And on the next slide, you will see how it changed. So even though like the ingress messages are still propagated in the same way as it was done before, now the consensus doesn't take, like the consensus artifacts such as blocks don't take as much bandwidth as before. We still do have 3 small spikes on the right. It's because we send a block to some of the peers, to the peers who, for some reason, didn't have all the ingress messages in their pools, in which case they had to request those missing ingress messages from me as a block maker, so I had to send them back to them. Yep, and like this is why we saw an improvement in the throughput. Thank you.
Awesome. Thank you, Camille. Very nice. Then we move to the third ingredient of the Stellarator milestone, and Luke is going to tell us all about that.
Yeah, hi everybody. Here's Luke from the Motoko team, and very exciting news also from Motoko side. As you probably know, Motoko has this property of orthogonal persistence, which actually means your program is a database. So all the program state that is in Motoko, it's technically speaking, it's all objects that are directly and indirectly reachable from the main actor. Variables, so-called stable variables, is automatically retained across upgrades. So no libraries or specific things to be considered to get that persistence. While this is actually a nice feature, it used to be not like optimally implemented. It was the mechanism behind the scenes was quite inefficient and also non-scalable. So the reason for that is that how we did that. So on an upgrade, the program state that is in main memory was actually serialized, like copied over to stable memory. Then the actual upgrade happened where the main memory was erased for historical reasons, especially because even the main memory is file backed on the blockchain, on the ICP. And then later on, that this all happened automatically. The stable state got deserialized back. So the problem is when the program state grows, then this serialization takes a lot of time, and the time may be even more than can be accommodated by an upgrade message, so that people then notice this instruction limit's been hit and then got stuck. So now on the next slide, this has been substantially improved. We made a very simple move, which was still technically involved to get that realized. So this was a change on the ICP and also on the compile and runtime system of Motoko. What we did, instead of discarding the main memory on an upgrade, we somehow made the main memory, instead of being a RAM, so to speak, transition it to non-volatile main memory. We just keep it around. So on an upgrade, Motoko does do nothing with the main memory state, except that it tests that the new program version is completely compatible with the old version. We even allow like implicit migration, some automatic changes can be automatically done. And if people have like more complex changes or migration, this can be manually implemented. But everything is safeguarded, so there can be no data misinterpretation or data corruption. So this actually then obviously simplifies things, but at the same time also gives us a tremendous improvement in scalability. So the upgrade is instantaneous, and at the same time, accesses to the presumed stable stuff or persistent stuff has the same performance than on main memory. And then yet another part, we extended the main memory to 64-bit, meaning that in the future, we are ready to scale to the same size than stable memory. And that's all the exciting news from Motoko. Going back to Manu.
Very cool, Luke. Thank you. This was all Stellarator milestone. Let's move to the third milestone quickly that we reached in this month, which is the Beryllium milestone, which I said was about simplicity. And so we all know that writing software is hard. It's easy to introduce bugs, and we want people to write more and more advanced applications on ICP. So we want to make sure that we give developers all the tools that they need to be successful at writing correct advanced applications on ICP. And we can summarize the things that we added for Beryllium in kind of 4 things. The first is that now there is the ability, the protocol supports taking canister snapshots. So you can ask the protocol, please take a snapshot of my canister. And this will take a full backup of everything. And so you can now, for example, take such a snapshot, do an upgrade, and now if something were to go wrong with your canister, maybe you had a bug in your new code, you can roll back to that snapshot and be in a good state again. So I think this will help a lot of developers have more peace of mind. We also introduced logging functionality. So of course, you could always keep your own logs in your canister code. But one particular challenge is that if your canister runs into an error, there's a trap, then your state is rolled back, which is a good thing, right? That's by design, we want that. But it means also you cannot log there. So you don't really know what's going on and you might miss it. And now logging, with logging, you can additionally log such errors that you run into along the way, which will very much help developers observe issues and fix them before it bothers too many users. Backtraces were also added. So now when your canister runs into an error, you get a backtrace, so you know exactly what call tree, what state your program is in when it reaches a certain error, which will go a long way into debugging and fixing the issue. And we improved how we made error messages more actionable. So we gave them better descriptions, better hints, and links to documentation. Again, trying to help developers build correct and reliable software on ICP. So that's our 3 big milestones that we reached. Just to very quickly recap, so with Tokamak, we get a 50% latency reduction for ingress messages. With Stellarator, we now have 0.5 terabyte of stable memory per canister and 1 terabyte of memory per subnet, thanks to this new storage layer. We increased the ingress bandwidth per subnet by a factor of 3, so you can much more quickly get data into your canister. And we have the seamless and scalable persistence in Motoko with the enhanced OP. And with Beryllium, the simplicity, we added support for Canister snapshots, logging, backtraces, and improved the error messages. And so this combined, I think, really makes a big step towards really move the needle in what you can build on-chain, on ICP. I'm very proud of this effort, and this was, of course, a huge team effort. So a big congrats to everybody that contributed to this. I think it really, I'm very proud of these results. And also, I want to the ICP developers, please think about these changes. You have a lot of new capacity and features available to you, so think about how you can use them. And I'm very excited about what you can build with this. I put some links here. There's technical blogs on Medium that you can check out to learn more. There's a very nice video by Dimitris that showcases how you can use the new Beryllium features to debug your Canister. And that's it. Thanks, everybody.
All right. So yeah, I'm here, Roel Storms from the Product Security Day, from the Product Security team. And I'm here today to present one of the newest security best practices that we have written and published on the Dev portal. This one is on how to securely integrate mobile applications with internet identity, which apparently was pretty tricky to do so once we started researching it. So that's why we wrote it down. It explains the risks when doing so, and it also introduces a new design that can mitigate these risks. For most of you that know this, II authentication protocol is somewhat different from traditional Web 2 protocols like OAuth. So natively, it can't integrate with mobile apps. And yeah, we've seen some vulnerable implementations. So hence we wrote a security best practice for the future. How is this realized? And that's what the rest of my presentation is going to be about. But very briefly, we introduce a proxy web application that can actually do the II authentication and with which our mobile application can interact. We also had to add an intermediate session key to keep everything secure. And we have to protect the delegation that II generates. You can find the best practice under the QR code, but I'll share that at the end as well. Before I can actually explain the issues, let's briefly talk about ICP authentication. So this is even without II. If you interact with the internet computer, or if your users interact with the internet computer using your application, then your application will typically generate a key pair using agent.js and will sign all the messages, and those signatures can be verified. When your Canister sees such a message, it will often want to see who is the caller of the message, who is the identity making such a call. And for that, it will have to verify the signature and check the principal. And this principal is correlated to the key pair that's generated over here. So you can immediately see a problem. If I have multiple devices, I will have multiple of those key pairs. And that means I have multiple principals. So I don't really have a stable identity. And this is exactly what internet identity can solve for you. How does it do that? Well, this session key that you generate in the front end will be signed by the II Canister to confirm that you own a certain internet identity, a certain anchor, or a certain principal, what do you want to call it. And this attestation by internet identity is what we call a delegation, in this context at least. It obviously requires a user to authenticate with II, otherwise such a delegation is not delivered. And this flow, this authentication flow, is initiated by your application using, yeah, no, that's not really relevant. So once the application in the front end has such a delegation, it can create valid signatures, and these can be sent in the messages to II. What is noteworthy is that such a delegation, such an attestation report is scoped to your application. It is scoped to your origin. And this helps with security, but also with privacy. So in the diagram below here, you can see what that looks like. You have the II user key. This is managed on chain by the II Canister. And this is delegated to your temporary session key, which eventually signs all of your requests. And this II user key is stable, and therefore you always see the same identity on your Canister side. So if you look at it in a sequence diagram, that's what it looks like. If the user wants to log in, a session key pair is generated. You then ask the II to generate a delegation, to generate such an attestation report for that session key using the normal II client authentication protocol. If your user is not authenticated yet, then probably it is required to authenticate with something like a passkey. And then when everything works well, a delegation is requested from the II Canister backend. This delegation, in this normal flow, it's not really a sensitive element, so no confidentiality requirement whatsoever. It can just be returned to the DApp frontend, and now the DApp frontend can use the session key and the delegation to make authenticated requests towards your Canister backend. Notice that this return flow uses the browser's post message API to communicate this piece of information securely back to the right web app that is running in the browser. And that is also immediately the issue with that, is that this post message API to return the delegation is only supported in browsers, so mobile apps don't have access to it, which limits authentication to web apps. The solution is pretty obvious. It is to introduce some web application front end in the middle there that will do the II authentication protocol for you. So let's go back to the sequence diagram to see what this looks like. We have our same three components on the right side, but now we have a mobile application that wants to talk to the II. And for that purpose, we have this proxy web app in the middle. Now it is the mobile app that generates a key, because of course the mobile app will eventually want to make calls towards your Canister, so it needs to have this key. It will then, through a mechanism that you need to develop, ask the proxy web application to obtain a delegation for this key. And it is then up to the proxy web app to do the standard II client authentication protocol. The result of this is that, again, a delegation is obtained. All of this stuff on the right is just standard II stuff. And then this delegation can be returned back to the mobile application. So this is, if you implement a solution naively, this is what you come up with. Now, there are some issues with this. And there's different ways to exploit this, but the easiest one to think about it is if the user would have installed a malicious mobile application on the same device. This malicious mobile app can also generate a key pair, and it could also request the proxy web app to initiate such an authentication flow, because the proxy web app is not capable of authenticating this request that comes in. So your malicious application would load the proxy web app, asking it for its session key to initiate a client authentication protocol. The proxy web app would do that. The rest of it is the same story. The user is authenticated, a delegation is generated, and the delegation is returned. Now, the attacker needs two things to make authenticated calls. That is the session key, which it knows because it generated it, and the delegation. Now, the delegation is present on the internet computer because we have all of these different node operators with different nodes and subnets. And in theory, they could observe this delegation somewhere. But also, when the proxy frontend needs to return the delegation back to the mobile application, in this communication channel, this is like an inter-app communication on mobile devices, the delegation could leak. And if that were to happen, then the malicious application, the attacker, can make authenticated calls and thereby impersonating the user. So it's clear all of this involves a phishing attack, right? The user needs to install a malicious application and go along with this flow. The user also needs to authenticate him or herself, but the way this looks in practice, it's very easy to get confused because this proxy web app just redirects you. So it's not very noticeable what's going on here. Typically, you just see the II front end, and if you're not very careful about it, you would just go along with the authentication flow. How can this be solved? This is the same diagram as we've seen on the second or the third slide, but now we introduce an intermediate key. And this intermediate key pair is only known by the proxy web application, and without it, this entire delegation chain from the II user key to the session key on the mobile device is not usable. Let's see how this actually solves things. Again, on our sequence diagram, the mobile application generates a session key, loads the proxy web app with that session key to initiate the II authentication flow. But instead of doing that directly, the proxy now generates its own key. And the proxy will initiate the II authentication flow using that intermediate key. The rest of it is standard II stuff. So a delegation gets generated. But even if this delegation were to leak to the attacker, it's useless because the attacker has the delegation, but only his own session key. And this delegation delegates from the II user key to the intermediate key. So you would need that intermediate session key to make any signed requests to the internet computer. Of course, this also means that our legitimate mobile application cannot use the delegation. So what does the proxy have to do? It needs to construct the full chain from the II user key to the session key on the mobile application. And it can do so, and it can return it back to the mobile application. So in this last step, we have the full delegation chain, which is, again, sensitive. It needs to be kept confidential. If not, if this were to leak to an attacker, then again, he has the full delegation chain and a key to make signed requests. So as I said earlier, the delegation on the right side is not sensitive. It can be stolen by someone. The delegation here needs to be kept secure. And this is luckily feasible on mobile devices if we use the secure inter-app communication mechanisms, which is app links on Android and universal links on iOS. There's slightly more to it as well, which you can read in the security best practices. And I mean, this is a lot of information, so I'd advise you to open it up. If there's one takeaway from this, that is then if you ever want to integrate a mobile app with II, go read this document, reach out to us on the forums or in chat if you have any more questions. I'd also like to thank Thomas Muller from our team because he actually came up with this design. And I'd like to thank Robin, Frederick, and Jesse for contributing to the security best practices.
Yeah, hi everyone. I'm Alex from the message routing team, and today I want to present you the progress on asynchronous checkpointing. With this project, we improve handling larger states, mostly number of canisters and higher loads. It's scheduled as a part of the flux milestone. The problem we're solving is free pauses in responses to users' calls during checkpointing. So when we create checkpoint, I will explain what it is on the next slide. We don't respond to the user's update call, so they have to wait. It's user visible latency, and it's better to have it as short as possible. And the duration of this pause grows as the subnets grow in states, in particular number of canisters. In order to solve it, we measure the duration of checkpointing steps and move them from critical path to be executed in parallel in background, hence asynchronous checkpointing, asynchronously from execution. Next slide, please. So as you know, the internet computer consists of subnets, and all the nodes of each subnet have exactly the same state bitwise, and we serialize the state to disk every 500 rounds. We do it for a number of reasons. One of the reasons is if a new node wants to join, it has to fetch this state from other machines, put it on disk, deserialize, and start execution. Another is if a machine reboots, for example, due to power outage or due to the replica upgrade, the weekly upgrade. And the third reason is to ensure that the nodes don't diverge. So when we serialize all the state to the disk, we run more extensive checks, and we check that the state across all the machines is the same. So if it does diverge, for example, that can only happen due to software bug on the replica side, that we notice this as early as possible. Next slide, please. So the challenge is the state's size and number of canisters. So we can have hundreds of thousands of canisters, and the state size, as presented earlier before, can be up to 1 terabyte. So a naive approach would be to just dump all the state to disk every 500 rounds, so that's every few minutes. But we cannot afford it for performance reasons. So we have number of optimizations to speed things up. And yeah, so the state size grows so naturally, and if we don't update our system, the checkpoint duration will also grows, and it leads to user visible latency. That's why we need to constantly improve performance to keep up with the natural scaling of the system. Next slide, please. In asynchronous checkpointing project, we identify heavy stages and refactor the code to make them executed in background. And we make sure that we don't break anything, which is the most of the work. It became possible because of the LSMT, as presented by Stefan previously. I tried it once 2 years ago, and I could make things executed in the background, but then it didn't improve performance because of the old storage layer that was just stalling in the kernel, and the asynchronous stages still stall the execution, even though they shouldn't. Next slide, please. We have already rolled out, as for last week, the first stage, which is lazy loading of the page maps. Page maps represent canister memory, both heap and stable memory. We have hundreds of thousands of canisters, hence hundreds of thousands of files, of page maps files. We used to load them every checkpoint, all of them, all hundreds of thousands, which took a while. Now we only open them once the data is necessary for execution. And because most of the canisters in subnets with many canisters, with hundreds of thousands of canisters, are idle, we don't ever open them. Next slide, please. This is the effect on checkpointing duration on OpenChat. This is the rollout from the last week, and as you can see, it immediately sped things up by a factor of roughly 1.5, and the effect is larger on the slower nodes, which I find good. Next slide, please. Also, it reduces the pressure on the kernel. We used to open almost 500,000 of files, and Linux kernel can do it, but it certainly pushes it into less tested territory. And we are quite happy that the number of open file descriptors plummeted. Next slide, please. Yes, so that's it for what is rolled out already. And at the next, it's just one part of the asynchronous checkpointing, and the next steps in the coming weeks, we will move even more stages to the background. Most interestingly, ones related to the future messaging models. So in future messaging model, we plan to allow for more messages, and we also deserialize the messages. If we make these steps in background, it will allow us to handle larger message queues without performance issues. That's it from me. Thanks.
Thank you, Alex. Thanks for the update on the asynchronous checkpointing. And last but not least, what Kyle waited for the whole meeting is the TAP protocol demo.
Okay, cool. Yeah, thanks everyone for giving us the opportunity to present how that actually looks in the wild. That all that amazing stuff that you're basically enabling us to do. I'm Marcus from the TAP protocol. In our community, I'm also known as the persona Benny. Yeah, but I'm fully doxed. Marcus Bob. Nice to meet you all. Let me quickly explain what the TAP protocol actually is, and then we move later on what it actually does and how ICP comes into play with that to enable what we're doing. So the TAP protocol is basically a meta protocol that sits on Bitcoin ordinals. It's comparable to the BRC-20 protocol. It shares some similarities on the surface level. But it goes far beyond that. And what we are actually trying to achieve, and actually achieved that already, is to allow things like programmability on an L1 layer, yeah, which then includes also fulfilling different characteristics that people see like you're operating on an L1. And So the problem that we were facing when BSC20 came out, and later even with Runes, is that the assets themselves, they are not really programmable like we are used to, let's say, on other chains that have native smart contract support, and hence there's no such thing really like advanced DeFi, GameFi, metaverses, and that kind of stuff. And this is partially, but not only, because of how rigid the different token standards are. One classic example of the rigidness is, for example, if you would simply want to trade any kind of token, yeah, then you would need BSC20 and Roots. It's the same. You would need to create packages of tokens of money, and then you would put that out. There are some, let's call it, yeah, don't want to call it hacks, but innovations, yeah, that seek to somehow mitigate that through several types of algorithms. But if you really want to operate in a way that allows for general programming purposes, we found that this is not really feasible to do, because you have an enormous amount of complexity to challenge just for simple use cases like trading. So instead, what the TAP protocol then does is it allows for more expressiveness within the protocol, which means that you can not only do more than you can do, for example, with BSC20 and Runes, talking about simple and cost-effective airdrop mechanisms, but also allows for a from ECDSA based voucher redeem system. And the difference to the other approaches here is that instead of having roll-ups, yeah, and leaving basically all the infrastructure that you already operate on with L1, for example, the ordinals wallets that people are using, we're going basically the approach to utilize qualified systems to integrate through oracles the TAP protocol, and then operate on these systems with their smart contract capabilities. And of course, when you're identifying systems that actually allow for the most, let's say, integrated features and capabilities to actually reach that goal, we were internally figuring what people feel is actually operating on L1, yeah. There are some lower level kind of features that would suggest that, for example, that whatever you're doing on Bitcoin L1 is needs to be done on UTXO level. So you need to be able to utilize the UTXOs natively, right? But it can go so far as saying like, okay, who's actually getting the rewards, yeah, for mining a block, yeah. If it's on L2, it's not the Bitcoin miners, right? So there's a whole range of things what people think an L1 is, and we classified the different opinions on that, yeah. And we're putting that basically into one list of requirements that we need to fulfill, that this is seen as an L1 solution. And by doing the research, we found out that ICP is actually the one that fulfills all these criteria. It allows for direct Bitcoin interaction. You're not exposing your private keys, yeah, that actually the canisters are working with. When you run canisters, it allows for HTTP outcalls, which is in our case pretty important, because we are using an Oracle-like system. It's basically an API, yeah, but it's also be able to be oracleized on other chains. And last but not least, it's scalable and secure, yeah. So, and that made it pretty easy for us to make the decision, yeah, to utilize ICP in our mission. And on top of all that, huge shout out also to the Azel team. Yeah, you probably know Azel. That project provides basically TypeScript integration. We have really great feedback from other developers, from our community, makes it really easy for them to get started, like on a productivity level on ICP. So, and having that achieved just recently with two to us very important L1 based integrations into ICP, namely a TAP protocol to Ethereum bridge, fully running on ICP on the smart contract level, as well as an AMM swap, yeah, that also combines all these concepts and all these strategies that I was talking about previously. And by that, we are able to do like many of the things that are listed here. Of course, it's multi-chain integration that we're achieving, hence the bridging. We can also start to use our account abstraction, yeah, or our version of account abstraction. That's actually pretty important to us as well. Things like providing developer-friendly environments, yeah, things like that. And just to showcase how that looks in the wild with an actual AMM swap, is here in this little video. So what you see here is basically Taparu swap. Yeah, it's a pretty neat thing, and it's very important to note that when you connect here with a wallet, yeah, you're actually using a Bitcoin wallet. ICP is literally working in the background. It's like an awesome workhorse that makes that possible. Yeah, so people can transparently utilize ICP, yeah, and have literally a trust minimized bridge, or in this case an AMM swap, and can fully operate swaps literally like Uniswap v2. Yeah, that's basically how it looks like. There's the TAP wallet being connected. You select the token, yeah, that you want to trade into. You select an amount, then the balancing is done there for you already. You create an order, you pay for the actual inscription, yeah, you sign and pay. Of course, you have the transaction pending, takes usually like 10 minutes as we know and love on Bitcoin, right? And then the swap is completed. So that's basically how that looks like as a quick overview, how that actually looks like in the wild. It's pretty nice. So, and what we were able to achieve with ICP was the first ever Bitcoin native smart contracting. Now that's literally the first time that you didn't need to do any kind of roll up, that you didn't need to come up with your own L2 solution, yeah, that you forked from somewhere else. You could literally like get into the action and do your stuff. So you already started to be productive for what you want to achieve, namely in our case, operating on Bitcoin L1 to get these kind of things done in a trust minimized manner. So, which then of course includes then the first ever AMMs and pool swaps. The advanced account abstraction is something that's getting more advanced even over time. Yeah, but that's TAP protocol specific. And like I was mentioning before, the first Bitcoin to Ethereum bridge, TAP Bitcoin to Ethereum bridge. What we now have in the works is an actual stables bridge from Ethereum into the TAP protocol. So we will basically see then things coming together. Another thing that's in the works right now is native asset staking, where we will use the ICP infrastructure as well. And yeah, and it has been a pretty amazing experience so far. And when it comes to L2 and having like a lot faster finality and things like that, and actually using, for example, ICP identities, this is also in the plans for the first quarter of 2025, which means that that we will then also offer a fast action kind of swap on Taproot swap, for example. Yeah, so we just wanted to start with L1 first, because L1, that's in the Bitcoin space, it's the thing. Yeah, who's not only doing it first, who's also doing it consistent, who's able to create not just a one-off product, right, but who's able to and also make other developers, yeah, to make more, yeah. And there's a lot going on right now in our community with our development, and I would really like to thank you again for the ICP team to make that possible, as well as Azel, yeah, huge shout out there as well. Can only ask to people who don't know that to look into that. Yeah, and yeah, that's basically the presentation. Hope you enjoyed that, and if you have questions, anytime. Thank you.
We did. Thanks, Marcus, for the kind words. I want to also thank all the presenters. That's for today, and I want to wish everyone a nice rest of the day. Thank you all.